Step into any large building, a hospital, office, or mall, and you'll notice the comfort right away. But behind that comfort is a network of sensors working quietly to keep the air just right. These sensors are the backbone of every HVAC system, feeding real-time data to the Building Management System, or BMS, so it can keep everything running smoothly. Without accurate sensors, the BMS would be flying blind, leading to wasted energy and uncomfortable spaces. In this chapter, we'll quickly explore what HVAC sensors do, why they matter, and how choosing the right ones makes all the difference. Ready to discover the unsung heroes that keep our buildings comfortable and efficient? Let's dive in. What exactly is an averaging temperature sensor, and why do we need them in modern HVAC systems? Let's dive deeper into the different types, their specific uses, and where you'll find them in a building. Picture a massive air duct in a commercial building. If you only measure the temperature in one corner, you're missing out on what's happening everywhere else in that duct. That's why averaging sensors are so important, especially in large or complex HVAC systems. The air inside these ducts isn't the same temperature throughout. There are warm patches, cool spots, and everything in between, all swirling together as air moves through the system. Averaging temperature sensors are designed to solve this problem. Instead of taking a single reading, they stretch a sensing element, like a long probe or flexible tube, across the entire duct, sampling temperatures at multiple points along the way. This way, you get a blended, accurate average of the whole area, not just a single spot. Think of it like upgrading from a blurry, pixelated image to a crystal-clear photo. You're not just seeing one detail, you're capturing the full picture of what's really happening inside your ductwork. The most common type of averaging sensor is the capillary tube. This is a long, flexible tube, often filled with a special gas or liquid that reacts to temperature changes. As the temperature varies along the tube, the sensor averages out those changes to give you a single, reliable reading. Capillary tube sensors are especially popular in large air ducts, air handling units, and mixing boxes, where temperature can vary widely across the cross-section. There's also a more modern approach, electronic averaging sensors. These use several digital sensors spaced out along a wire or cable. Each sensor takes its own reading, and then the system calculates the average of all those points. Electronic averaging sensors are ideal for integration with building management systems, and they're often used in high-tech facilities or where precise control is needed. Another type is the rigid rod averaging sensor. These are solid rods with multiple sensing elements embedded along their length. They're perfect for applications where a flexible sensor isn't practical, such as in smaller ducts, valve boxes, or where a straight installation is required. So, where do you mount these sensors? Averaging temperature sensors can be installed in supply air ducts, return air ducts, mixed air plenums, air handling units, and even in outdoor air intakes for large systems. The choice depends on what you need to measure: supply air for delivered temperature, return air for room conditions, or mixed air for system efficiency. Both capillary tube and electronic types feed their data into the Building Management System, or BMS, providing a true average temperature for the entire duct. This helps the system make smarter, more efficient decisions about heating, cooling, and airflow. Choosing between a capillary tube, a rigid rod, or an electronic sensor depends on your specific needs. Capillary tubes are simple and reliable, rigid rods are sturdy and great for straight runs, while electronic sensors can offer more precision and easier integration with digital systems. The key takeaway is this: to truly understand what's happening in your ductwork, you need to measure the whole area, not just a single point. Averaging sensors, whether capillary, rod, or electronic, make that possible. With accurate average readings, your HVAC system can respond more efficiently, keeping temperatures comfortable and energy use in check. When you have the right information, you can make the right decisions, whether you're troubleshooting, optimizing, or just keeping things running smoothly. That's the foundation of a well-functioning HVAC system: reliable data, smart controls, and consistent comfort throughout your building. Now, if you're installing a flexible averaging sensor like a capillary tube, there are a couple of practical details to keep in mind. For beginners, it's important to use enough capillary clips to secure the sensor evenly across the duct. A good rule of thumb is to use one capillary clip every 12 to 18 inches, about 30 to 45 centimeters, along the length of the sensor. This keeps the sensor in place and ensures it's exposed to the airflow throughout the duct. You'll also want to create several bends or zigzags with the sensor as you install it. Typically, you should plan for at least 3 to 5 bends depending on the size of your duct. These bends help the sensor sample air from different parts of the duct, giving you a more accurate average temperature. For rigid rod sensors, Make sure the rod spans as much of the duct width as possible and is mounted securely to avoid vibration. Electronic sensors should have their sensing points distributed evenly, and cables should be routed to avoid interference with airflow or maintenance access. So, for a standard installation, expect to use multiple capillary clips spaced evenly, and make sure to create enough bends to cover the duct area effectively. This approach is simple, but it makes a big difference in the accuracy of your readings. Remember, keeping it simple and effective is the best way to ensure your HVAC system works for you, not against you. And by choosing the right type of averaging sensor, mounting it in the right location, and installing it correctly, you'll set your system up for long-term success. In ductwork, especially at the mixed air plenum, temperature can vary wildly. If you don't measure it accurately, you waste energy and make people uncomfortable. The key? Select an averaging sensor long enough to cover the duct's cross-section. Don't guess. Check the mechanical drawings for duct dimensions. For big ducts, install the sensor in a zigzag pattern to cover the area. Rule of thumb: 1 foot of sensor for every square foot of duct area. Too short, and you miss spots, leading to bad readings and higher costs. Do your homework, measure, calculate, and choose the right length. For example, a 4x 5-foot duct needs a 20-foot sensor. Don't just grab a standard size, pick what fits. That's how you build a system that works and lasts. Next, let's walk through sizing step by step. Precision here pays off later. Let's break down step by step exactly how to calculate the right length of an averaging sensor for any duct, using clear formulas and practical examples, so you'll always know what to do. And once you've got the right size, I'll walk you through the exact installation process to make sure your sensor works perfectly. Step 1. Review your mechanical plans and find the exact duct section where the sensor will go. Write down the duct's height and width at that spot. Even small differences matter, so double-check your numbers. Step 2. Calculate the cross-sectional area of the duct. Use this formula: area, SQFT, equals sign, height, FT, x width, FT. Make sure both measurements are in feet before multiplying. Worked example: if your duct is 3 feet high and 8 feet wide, plug those into the formula. Area equals sign 3 feet x 8 feet equals sign 24 square feet. This is a typical size for a large supply duct. Step 3. Use the industry rule of thumb: 1 linear foot of sensor for every square foot of duct area. Formula: sensor length, FT, equals sign duct area, SQFT. This ensures the sensor samples air across the whole duct. Example: calculation. For our 24 square foot duct, you'll need at least a 24-foot sensor. If sensors are sold in standard lengths, say 18, 24, or 36 feet, always round up to the next available size, never round down. Practical tip: extra sensor length is better than too little. If you have a 22 square foot duct and sensors come in 24-foot lengths, use the 24-footer. Never try to make do with a shorter sensor. Step 4. Now let's get into the installation details. First, make sure the duct is clean and accessible. Plan your sensor path so it covers as much of the duct cross-section as possible. The best method is to stretch the sensor in a zigzag or pattern from one side of the duct to the other, moving back and forth across the airflow. This layout helps the sensor sample air from all parts of the duct, giving you a true average reading. Common mistake: don't leave the sensor coiled up in a corner. A coiled sensor only measures a small pocket of air, making your data unreliable. Always spread the sensor out for full coverage. For installation, use mounting clips or brackets provided by the manufacturer. Secure the sensor at regular intervals, typically every 2 to 3 feet, so it stays in place and doesn't sag. Make sure the sensor is not touching the duct walls directly, as this can affect readings. If the duct is very large, you may need to use support wires or additional clips to keep the sensor suspended in the airstream. If your duct has bends or changes direction, add a little extra sensor length to cover the full path. For each bend, add about 1-2 feet to your total sensor length to ensure complete coverage. Carefully route the sensor around bends, keeping it as evenly distributed as possible. After installation, double-check that the sensor is secure, evenly spaced, and not pinched or kinked anywhere along its path. Connect the sensor leads to the control panel according to the wiring diagram, and label the sensor for future maintenance. When you size and install your sensor correctly, your system will deliver reliable performance, and you'll avoid costly troubleshooting down the road. Now let's move on to coils, the heart of your air handler. Sizing sensors for coils follows similar principles, but there are a few important differences to keep in mind. The same basic approach applies, but you'll need to consider the coil's unique shape and airflow patterns. Let's break down what's different and how to get it right. Ready to learn more? Let's see how sensor sizing works for coils and make sure your system is set up for success. Coils are where the real temperature change happens. Measuring air temperature as it leaves the coil is critical, especially for cooling coils to prevent freezing. Single-point sensors don't work here. You need an averaging sensor to capture temperature variations across the coil face. Freeze stats are often averaging sensors for this reason. Sizing is similar to ducts. Measure the coil's face area, height times width. Find these dimensions on the mechanical schedule or submittal data. For example, a 4-foot by 5-foot coil needs a 20-foot sensor. Always install the sensor on the downstream side, the air leaving the coil. This is where freezing or overheating is most likely. Cover the entire face for safety and efficiency. Next, let's see how to install these sensors for best results. Details matter here too. With the right sensor length, installation is all about coverage and care. When installing averaging sensors on cooling coils, start by measuring the coil dimensions to determine the number of passes needed for even coverage. Mount the sensor on the downstream face of the coil, stretched in a serpentine pattern. Begin at one corner of the coil and secure the sensor horizontally, making sure it is straight and taut. For a 20-foot sensor on a 4x 5-foot coil, make 4 horizontal passes, each 5 feet long, spaced evenly. Use a tape measure to mark the positions for each pass, ensuring consistent spacing from top to bottom. Keep the sensor 1-2 inches from the coil fins, close enough for accurate air temperature but not touching. Use spacers if necessary to maintain this distance along the entire length of the sensor. Use special clips to secure the sensor at each end and at intervals along each pass. Never tape or let it hang loose. Attach the clips firmly to the coil frame or support rods, not the fins. Plan your pattern before drilling or attaching anything. Mark the sensor path with a non-permanent marker to guide your installation. Avoid obstructions and ensure even coverage. If there are pipes or brackets in the way, reroute the sensor to maintain even spacing. A well-installed sensor protects your equipment and ensures accurate control. Double-check that the sensor is secure and that the wiring is neatly routed to the control panel. Take your time. This is where quality shows. Inspect each clip and connection to confirm the sensor is firmly in place and not at risk of slipping. Now let's talk about the small hardware that makes a big difference. When selecting capillary clips, choose a material that resists corrosion. Stainless steel is a popular choice for durability and longevity, especially in humid or corrosive environments. Make sure the clip material is compatible with both the sensor and the coil frame to prevent galvanic corrosion. Before you start, calculate the number of clips required for each coil. As a rule of thumb, use 1 clip at each end of every sensor pass, and additional clips every 18 to 24 inches along the length. For a 4-pass coil, that usually means at least 10 to 12 clips per sensor depending on the coil size and sensor length. Even the little things matter. Organize your hardware before starting to avoid delays during installation. Proper use of these clips ensures your averaging sensor stays in place for years to come. Capillary clips are essential for a solid installation. Use 2 clips for the first foot, then 1 per foot after that. For a 20-foot sensor, that's 21 clips. Space them about a foot apart and add extra at bends in your serpentine pattern. Clips prevent sagging, vibration, and contact with coil fins. Don't skimp. Using enough clips is a hallmark of quality. The cost is tiny compared to the value they provide. Secure, well-placed clips mean your sensor will last and perform. Do it right or don't do it at all. But what if you don't have the measurements you need? Let's tackle that next. Sometimes you don't have drawings or data, just the equipment in front of you. If possible, open the unit and measure the coil face directly. If not, measure the duct just before or after the coil. It's usually the same size. When in doubt, add a little extra to your calculation. If you absolutely can't measure, use a longer sensor rather than a shorter one. A denser serpentine pattern is better than missing coverage. Avoid guessing, but if you must, err on the side of caution. The goal, never come up short. If you only have airflow details and not the face area, estimate the coil face area by dividing the total airflow, CFM, by the typical face velocity, usually around 500 feet per minute for most coils. This gives you an approximate area, which you can use to size your averaging sensor. Now let's wrap up with a final checklist to make sure you get it right every time. Consistency is key. Let's review. Here's your quick checklist for sensor success. Always use averaging sensors for mixed air, discharge air, and preheat applications. Never use single-point sensors where air temperature varies. Size the sensor 1 foot per square foot of duct or coil face area. Do the math, don't guess. Always round up. Plan your serpentine pattern for even coverage. Mount sensors 1-2 inches from coil fins, never touching. Use capillary clips, 2 for the first foot, 1 for each additional foot. Space clips evenly and secure bends. If you lack info, measure directly or use a longer sensor. Avoid shortcuts. Quality matters. By following these steps, you're building a reliable, efficient system. The BMS depends on your attention to detail. That's how you make it right. Thanks for watching. Now go build something great.